Okay, so let's chit chat about these molarity problems, because it's also going to form the basis of the lab that you're going to do today. So let's make sure everybody's cool with this. So if you just stick with one idea, that molarity means moles per liter. Okay? And literally, trust me on this, if you just embrace that idea, then the problems all kind of fall into place. So if you look on that first problem, it says, what's a molarity of a solution in which 0.5 moles of sodium hydroxide is dissolved in 0.25 liters of water? Oh, okay. That was simple. You got your moles, right? You've got the volume. That's already in liters. Okay? So all you have to do is take 0.5 and divide that by your volume in liters. You're going to get a number. Put a fancy M on the end of it. That's your molarity. Okay? That one's simple. So then on number 2, it's just a little bit more complicated. Why is 2 a little bit more complicated than problem number 1? Yeah, but what's the relationship between cubic centimeters and liters? Yeah, there's 1,000 cubic. So what I would do is that you still got this 0.5 moles, right? And then you've got 480 cubic centimeters. Well, there's 1,000 cubic centimeters in 1 liter. Your cubic centimeters cancel out. So basically, you're going to take 480. And you can divide that separately. If you want to take 480 and divide it by 1,000 and get that number, or you can work it all in one step. Doesn't make any difference. You're still going to get the same answer. So what you should see, if you think about this, that your answer to number 2 is going to be a little bit bigger than your answer to number 1. Because in both situations, you have the same number of moles. But in problem number 2, you have the same number of moles, but you're dissolving that in a slightly smaller amount of water. So the concentration is going to be a little bit higher. Okay? Because it's the same number of moles, smaller volume, concentration is going to go up a little bit. Now, when you get to number 3, 3 is even a little bit more complicated. Please get 34.6 grams of sodium hydroxide dissolved in 220. So here's the deal. So start with this. You got 34.6 grams of sodium hydroxide. So what's the first thing you're going to have to do with the grams of sodium hydroxide? Mr. Peterman, what are you going to have to do?
Cancel out the grams on the bottom, right?
Fantastic. I'm going to get rid of the grams, right? And then I'm going to put 1 mole up here. So on moles, okay, bless you. You're starting up here in mass, and you want to go into moles. So, Mr. Peterman, am I going to use avocado's stand or the periodic table?
Periodic table.
Yeah, I want to look at the periodic table. I want to look at the molar mass of sodium, the molar mass of oxygen, and the molar mass of hydrogen. Okay, I'm going to add those numbers together. And I'm going to have a number here. Okay, molar mass. Just like you've done before. You just take grams, convert that into moles, boom, there you go. Then you've got the 220 cubic centimeters. Okay, and again, if you want to work this in one step, and there's 1,000 cubic centimeters, 1 liter. If you just want to shortcut this and just write that as 0.220 and not do that conversion, I'm cool with that. I know you all are capable of dividing by 1,000. Okay? Whatever process works best for you. So what you should see on the number 3, you should get a molarity on number 3 that's a pretty good solid GPA. Okay? So you should get a pretty good GPA on number 3. Okay? Cool with that. Now, when you get to number 4, okay? So 4 is the same process. What's a little bit more complicated on number 4 is I made these kind of a little more progressively complicated, okay? So you got 34.6 grams of magnesium nitrate. So notice on this one, I had the exact same mass I purposely did this. I had the same mass of sodium hydroxide as the same mass of magnesium nitrate. But what you'll see is that the moles of magnesium nitrate, even though it's the same mass, is going to be vastly different. Because the molar mass of magnesium nitrate is much bigger than the molar mass of sodium hydroxide is. Okay? So what you should see on number 4, even though you have the same mass and you're dividing it into a much bigger volume, you should see that your molarity on number 4 is less than 1. Okay? So your molarity on number 3 is around 4-ish. Okay? Your molarity on number 4 is going to be around 0 point something. Okay? So let's make sure everybody's cool with the molar mass of this magnesium nitrate. So again, there's 2 ways you can do your nitrates. You can do the nitrate by itself, okay, and then double that, or you can sit there and go, oh, I've got 2 nitrogens and 6 oxygens, okay? I don't care what you want to do. That's up to you. Personally, I always find, I find the mass of the nitrate, I write that on my periodic table, and then I just multiply that by 2, okay? If you want to go through and do it the other way, it doesn't make any difference. You just have to pick the method that works best for you. So what you should see on number 4, that mass of that molar nitrate, of that magnesium nitrate, is 148.3 grams. That's what you should have as the molar mass of that magnesium nitrate. Now, when you're doing these, okay, if you're going to divide and conquer, if you're going to find the moles of the magnesium nitrate by itself, don't round that too much, okay? You want to keep like 3 or 4 digits. If you're going to do these separately, you want to keep like 3 to 4 digits. So when you take that 34.6 and divide that by that 148.3, it works out like 0.233. Just don't write that down as 0.2. You've got to keep more digits, like, and then round when you get to the end, okay? So like on that, if you're taking those 34.6 grams and changing that into moles, when you do that, if you're going to do that as a separate step, keep like 3 or 4 digits, okay? Do not round that number, okay? You can round it to 3 to 4 digits, but don't round it to like 0.2, okay? You always want to keep more digits and then round when you get to the end. Now, when you get to number 5, okay? So here's the problem on number 5. So let's say, and on number 5, here's a 1 liter bottle, and I want to make up a 2 molar solution of potassium nitrate, KNO3. It's one of the solutions that we use a lot. Potassium nitrate is a white granular substance. So, and this is why we're going to do the lab that you're going to do today. Because you kind of got to visualize what's happening, okay? So, I'm going to have this liter of water. And because of the fact that it is a 2 molar solution, that means within this volume, I have to put 2 moles, okay? So what? I have to put in 2 moles. But here's the problem. In what units do your electronic balances measure in? Moles or grams? Grams. Scales don't measure in moles. If they measured in moles, simple. I would just take some potassium nitrate, I'd set the scale to potassium nitrate, I'd measure it out until it equaled 2 moles, boom, I'm done, okay? And I would just add that to that. But the scale, and this is the fundamental mindset that you have to get, is that the scales don't measure in moles. The scales measure in grams, okay? So, here's the deal. So, you've got 2 moles of KNO3. You know that 1 mole of KNO3 is gonna have a certain mass, okay? And you're gonna look at the periodic table and you're gonna find this number. So in this case, that's gonna be around 100. Okay? So 1 mole of potassium nitrate is around 100 grams. Okay, that's an ish, okay, but it's around 100. So what that means is that if I'm gonna make a 2 molar solution of this stuff, then I'm gonna end up with about 200 grams. But here's what's important. That's 200 grams per 1 liter. And conveniently, I'm gonna mix up 1 whole liter of this stuff, okay? So I don't need to do anything with the volume, because technically, that's about 200 grams per 1 liter. Well, if I multiply by 1 liter, because that's the volume that I'm gonna need, the liters cancel out, boom, I get grams. There you go. So your answer to number 5, here's how I want this answer written. It's like you're telling someone how to do this. I'm gonna say, hey, Grace, this is what I want you to do. You're gonna dissolve about 200 grams of potassium nitrate in 1 liter of water. So it's like an instruction, okay? So that's why I've got that line down there on number 5. When I say describe the preparation, it's like you're telling someone how to do this, okay? It's a sentence. You're gonna say, dissolve about 200 grams, and do not write about 200 grams, you're gonna calculate the exact answer. But your answer is gonna be about 200. So you're gonna say, dissolve about 200 grams in 1 liter of water. Okay, so that's how you're gonna answer that. Now, when you get to number 6, okay? So in number 6, I want a 0.4 molar solution of silver nitrate. Silver nitrate is AgNO3. By the way, if you ever work with a solution of silver nitrate, don't get it on your skin because it turns your skin black. So, and that's what they actually used to use for film before they had digital cameras. So, on silver nitrate, and again, here's what you have to visualize. So, you want a 0.4 molar solution of silver nitrate. And again, go back to this idea. That 0.4 molar means that's 0.4 moles per 1 liter, okay? That's what that number means, okay? That's what the number means. Now, in case you haven't figured it out, you got to get rid of the moles. So you can come down here and go, okay, that's 1 mole. Look up the molar mass of silver nitrate. It's a big number, okay? Because silver itself is a really, really big relative atomic mass, okay? So the silver nitrate molar mass is around 170, okay? Pretty big number. So this number is about 170. Now, if you stop right now, okay, you would know how many grams, if you take 0.4 times 170, that's how many grams you would need to mix up an entire liter, okay? That's how many grams you need for an entire liter. But you don't need an entire liter of this thing, okay? You only need 0.4 liters. So the simplest thing to do then is to come out here and go, okay, one option, and I'm going to give you a couple of options, is that you come out here and you multiply by 0.4 liters. The liters cancel out, the moles cancel out, you get grams, okay? That's an option. So some people like to do this in one big step. They cancel out all the units, okay? That's an option, okay? Now the other option that you can do, because some people like ratios, so here's the other way that you can work this problem, okay? And this appeals to some of you, and I don't care how you think this through. Your other option is that you take 0.4 times the 170, and that's about 68 grams. So what that means is that you need 68 grams per 1 liter is going to equal X number of grams over 0.4 liters. Okay, so what, if you want to do this, okay, you do this step right here. You take 0.4 times the molar mass of silver nitrate, and you say, oh, that's how many grams I'm going to need in 1 liter. And then you set up a ratio. You go, this is about 68 grams per 1 liter. is going to equal X number of grams over 0.4. And by the way, these are just approximations. Do not use these numbers. This just tells you if you got close to this. Okay, this is not the actual answer. This is just a very round number. You got to do the math. So when on your sheet, so help me, do not write down 68. This is not the answer. Okay, it's close to that. That is not the exact answer. Okay, so you can either do it all in one big conversion, or you can say, oh, this is 68 grams per 1 liter is going to equal X number of grams over 0.4 liters. So here's how your answer on number 6 should play out, okay? You're going to say, again, this is a sentence. You're going to say dissolve, okay? And your answer, it should be around 28, okay? So on number 6, you're going to say dissolve about 28 grams of silver nitrate in 0.4 liters of water, okay? That's how it's going to play out. And then on number 7, 7 is the most complicated one because you've got to convert milliliters into liters in the 0.1 molar solution. And you got to do and by the way, that's calcium chloride. That's CaCl2. That is not carbon and iodine and 2 iodines. That's 2 chlorines. Okay? When you see Cl, that is not carbon and iodine. Some of you did that on one of the previous assignments. This is Cl2. Okay? And make sure when you're doing chlorine, make sure that you're doing 35.5 for chlorine. Okay? Do not round that to 36. Do not round it down to 35. When you're doing chlorine and any of these, make sure you go out to the nearest tenth. So if all goes well on number 7, okay, the mass that you're going to need on number 7, the mass of that calcium chloride is going to be around 0.3 grams. Okay, so if you do number 7 correctly, when you get done, the mass of calcium chloride that you're going to need is going to be around 0.3 grams. Okay, so that'll tell you if you're close. Now, on number 8, you got the 24.8 grams of iron sulfate. You got to figure out the molarity. So your molarity on number 8, you can take the grams, convert that into moles, divided by the volume. Your molarity on number 8 should be around 0.1. Okay, so when you get on number 8, you should get something around 0.1. Now, let's talk about number 9. So, on number 9, here's what's happening. Like, copper nitrate tends to have a bluish color, and that's what you're going to do in the lab today. We're going to use copper sulfate, and it has a nice kind of blue. All copper compounds tend to have a bluish tinge to them. So, here's what I want you to see on number 9. You're going to measure out 65 milliliters of 2.5 molar solution. How many moles of copper 2 nitrate are there in the 65 milliliters? So again, go back to this. That 2.5 molar means that you'd have 2.5 moles per 1 liter. That's what the number means, okay? That's what the number means. Now, you're only going to measure out 65 milliliters. If you do the conversion, divide by 1,000, you get 0.065 liters. So, your first answer on number 9, here's all you have to do. Take 2.5 moles, multiply that by 0.065, boom, there you go. That's all you have to do. That's how many moles there are. Then, on the second part, then you're just going to take those moles and convert them into grams. So, on number 9, your number of moles is around, this is a huge-ish, is around 0.2. And the mass is around 30. So that's about where your answer should be. Okay? Yay, nay, kind of got it? Getting there? Okay, yes ma'am.
I don't understand how you got your 28 on 6.
On 6?
Yeah.
Okay. So let me back up here, we'll start. So on number 6, first off, what do you have as the molar mass of silver nitrate? Because if that's wrong, everything is going to be wrong.
169.9.
Fantastic. Okay? Per mole. Okay, so you need that number, that's fantastic. So here's the deal. So on this one, you've got a 0.4 molar solution. That means you're 0.4 moles per 1 liter, right? So one option is that you go, well, 1 mole is 169.9 grams. Okay? So if I take 0.4 times 169.9, okay, that tells me how many grams I would have in 1 liter. Okay, if I were to mix up a whole liter of this stuff, that's how many grams I would need. Okay? But I don't need a whole liter of this thing. I only need 0.4 liters of it. So your last step then is to multiply by 0.4 liters. So then your liters cancel out, your moles cancel out, and you get grams. So one option, if you just want to work this all at once, you take 0.4 times 169.9 times 0.4 again.
I just forgot to multiply by the 0.4 liters.
Yep, you got to do that. Okay, got it? Good? Grand? Okay, at some point today, get that handed in. Miles, please stop that camera. Okay, so with this lab, we're going to use a piece of equipment called a spec 20. It's a highly sensitive piece of equipment. And so basically, how the spec 20 works is this. What it does is that it has a little opening, okay? And you'll see this, there's a little opening in the top. It's a little lid, you flip it open. And you're gonna put in that a very specific test tube designed just for use in the spec 20. It's called a cuvette, okay? So these are labeled spec 20 cuvettes. So how the spec 20 works is that it shines light through the cuvette, okay? And then over here, on the other side, there's a sensor that measures how much of that light goes through. So why this appears as a blue solution, and light is like a whole long lecture. Here's a short version of how light works. The reason you see that as blue light is because it actually absorbs every color except blue light. And the blue light is what gets reflected off. So hopefully at some point you've heard like the Roy G. Biv, the colors of the spectrum, red, green, yellow, all that good stuff. Know what I'm talking about. Have you heard of Roy G. Biv?
Yes.
Yes, okay. These are the colors of the spectrum. So what you see as any color is because of the fact that it actually absorbs every color except that one. So like Ethan's shirt appears black because of the fact that it's absorbing all of the light and it's only reflecting off a small portion of it, okay? White shirt, okay? That is just the opposite. That's reflecting every color. Your shirt is red because it's absorbing every color but red, and the red light is getting reflecting off, okay? So the fundamental particle of light is called a photon, okay? So a photon is this weird kind of bundle of energy. And there's two, and we're going to spend a lot more time talking about light, okay? So today I just want to introduce this concept of a photon. And light, as it's transmitted, has a certain wavelength. And wavelength is the distance between like troughs or crests. So this spec 20 operates on a very specific wavelength, 535 nanometers. You don't need the number, that's what I have it set. So when you go in there, you're gonna see a number on here that's gonna say 535. That's the wavelength of the light, okay? Don't worry about it, but it has to operate on a specific wavelength. So here's what's gonna happen. What you're gonna do is that you are going to mix up 3 different solutions, okay? So this is the instructions here. You're gonna mix up a 1 molar solution of copper sulfate, a 0.5 molar solution of copper sulfate, and a 0.25 molar solution of copper sulfate. And each one of these, you're gonna mix up exactly 20 cubic centimeters of this stuff. So what you've got to figure out, and here's the calculations that you've got to do. So you want to mix up 20 cubic centimeters of a 1 molar solution of copper sulfate. Okay? So the first thing that you've got to do is do the math. Okay? It's like, how many grams do we measure out? 5, 10, 0.4? I don't know. So that's the first thing that you've got to figure out. Then you're going to do it for 0.5, and then you're going to do it for 0.25. Okay? So what you're going to do, this is what you got to be able to do on this test on Friday. You have to be able to do this without thinking. So you got copper sulfate, CuSO4. You're going to go through and you say, okay, hey, what's the molar mass of copper sulfate? Add together the copper, the sulfur, the 4 oxygen. Boom, you're going to get that number. Then, from there, you're going to do these calculations. So, when you get done with those calculations, let me check them. Okay? Because if these calculations of mass are wrong, the whole lab is going to go wrong. Okay? So when you get those done, bring them up, let me check them, make sure those numbers are right. Okay? Now, keep in mind, you're not mixing up an entire liter of this stuff. You're only mixing up 20 cubic centimeters. Now, look at the instructions. When I type this up, notice that I wrote that as 20.0 cubic centimeters. That means when you're measuring this out, you get exactly 20 cubic centimeters, okay? You need exactly 20 cubic centimeters in that graduated cylinder. This isn't, notice I didn't say, oh, you need 20. That's whatever, something close to 20. When I say 20.0, that's a reflection of how good this measurement has to be. So, when you do these calculations, keep in mind your scales that you're going to use go out to 2 decimal places. So when you calculate this number, get them out to 2 decimal places in terms of the mass. So here's what you're going to do. You're going to take a beaker. You're going to add the copper sulfate. It looks like blue flour. Okay, it's a very, very fine powder. Okay, it looks like literally. This is like you took. It's just like looks like flour from a Smurf bakery. Okay, it's a very, very light blue. So you're going to measure out a certain mass of copper sulfate. Then you're going to take those 20 cubic centimeters and you're going to pour that in, and then take a glass stirring rod. Okay, you never stir with anything that's metal because the metal could react. So you're going to take a glass stirring rod, which you have in your drawer. You're going to stir that up. Boom, here you go. Then I'm going to give you 3 cuvettes. So you're going to take that first solution and you're going to fill it about 3/4 of the way full. Okay? Then you're going to dump the rest of that solution out, rinse your beaker thoroughly. Then you're going to measure out the mass to make up a 0.5 molar solution. You're going to add 20 cubic centimeters to that. Boom, there you go. Now, if you're clever, okay, you all are, there's at least 2 or 3 of you in a lab group, okay? It doesn't take 2 of you to stir a solution. It doesn't, okay? It's not that cool. It's like, we'll do some cool things at lab. Stirring a solution, watching it dissolve is not really high on the coolness factor. So what I would do is like, once you get that first one and you start stirring it, you have the mass, go back, get the second one, and get it ready to go. So, in other words, it doesn't take both of you to only do one step. Work ahead. Go, hey, I'm going to do this. You go start on this next step. I'm going to do this. You go, so that you're working ahead. So what's going to happen when you get done? you're gonna have three different kind of bluish colored solutions. One's gonna be, obviously the 1 molar one is gonna be much darker than the 0.25 molar, okay? You're gonna have to get this mixed up. Then what you're gonna do, the spec 20 is in the back corner, back lab table in that room. Once you get them mixed up, here's what you're gonna do. You're gonna bring those up to me, and you wanna wipe off the outside of the cuvette. Mainly because you don't want fingerprints on the outside of it or any distortion, because that affects the light that goes through. So on the back side of this, here's the data table that you need to fill out. So it's going to measure three things: transmittance, absorbance, and concentration. So concentration is basically a measure of the molarity. So if and this is a very, very sensitive machine, okay? So in theory, when you mix up that 1 molar solution and you put it in there, the concentration should read 1, okay? That's what it should read. But it does, with this machine, as sensitive it is, if you're off by just a little bit, you're going to get a different reading than 1. So don't flip out if you don't get exactly 1. My purpose of this lab is that, hey, can you get used to the spec 20? How can you measure out molarity? Can you mix up solutions? Now, your transmittance. Your transmittance is a measure of how much of that light passes through, okay? And your absorbance, oddly enough, is how much of that light gets absorbed. So some people make this is a horrible analogy, but it works, okay? So you can think of the copper sulfate as bears in a forest, and you're sending like 100 second graders named Timmy through the forest. And what your absorbance does is measure how many of little Timmys get absorbed by the bears, okay? That's the short version. And your transmittance is how many of the Timmys make it across. So this is one of the questions. So if you have pure water, okay, like this, okay, so let's say you have pure water, and you shine a light through it, how much of that light do you think makes it across? All of it or none of it? All of it. So what that means is if you have pure water, that's like saying here's the forest, and there's no bears to get the Timmies, okay? So if you have pure water, all the Timmies make it across because there's no bears. So you would have 100% transmittance. All the Timmies are going to make it through, and none of the Timmies are going to get absorbed by the bears. Now, if you have this, okay, where you have some stuff in it, now this is like saying there's bears in here. So what that means is that if I shine through some of these Timmies, some of those bears are going to absorb some of the Timmies, and not all of them are going to make it through. So you have a certain amount of concentration like this. So if I do this and I dilute it, okay, so we'll do this, put some more water in there, okay. So as I make this more and more dilute, it's like I'm taking bears out of the forest, and more of the Timmies are going to make it across. So what this machine does is that it keeps track of basically the photons are like the Timmies, okay? That's, you're sending Timmies through the forest. Copper sulfate is the bears. The more bears there are, the darker this is going to appear, the fewer Timmies make it across, okay? So if you can visualize Timmies going across a forest full of bears. So what you're going to do is that you're going to bring this up. You're going to have your 3 test tubes. We're going to wipe off the outside of each one of them. We're going to put that inside the machine, okay? And then we're going to run through and we're going to measure. The machine's going to tell you 3 values: your transmittance, your absorbance, and your concentration, okay? And then we're going to do that for the 0.5, and we're going to do that for the 0.25, okay? Now, as this solution becomes more and more dilute, what do you think should happen to the transmittance? As you go down from 1 to 0.5 to 0.25, do you think your transmittance, which is the number of timings that are making it across, do you think that transmittance is going to go up, or is that transmittance going to go down? Keaton, what'd you say?
Up,
Why?
because there's gonna be less bears in the water.
Yeah, there's less bears in the water, more timings are going to make it across. Okay? Now, but what's going to happen to your absorbance? Your absorbance is going to go up or down. Your absorbance is the number of timings that are getting eaten by the bears.
Down.
Down, because there's going to be fewer bears too. So what you see is an inverse relationship. So as you go down, your transmittance should go up and your absorbance should go down because your concentration is becoming smaller. Now, I'm going to give you a half sheet O graph paper. Okay? Everybody's going to do their own. What you're going to do is that you're going to draw a graph down here on number 2, and you're going to place absorbance on the x-axis, and neither one of these have any units. It's rare that we draw a graph and they don't have any units. So here's what your graph is going to look like. You're going to put absorbance here, and you're going to put transmittance here. Okay? And you're going to draw this graph. You're only going to have 3 data points, okay? But what you want to do is draw a line of best fit. These have no units. Most of the time, when we're talking about units on a graph, this is one of the rare instances that there are no units, okay? These are just numbers, okay? It's transmittance, it's absorbance, so it isn't measured in anything. So, then you're going to calculate your experimental error. So down on number 1, and I give you this formula. Now technically this is like an absolute value. So you're going to have an absolute value of your theoretical minus your experimental divided by your theoretical times 100. So like on that first one, you should theoretically have a concentration of 1. Okay, that's what you theoretically should get. So on that first one, you're going to take 1.00. Let's say you put it in the machine and you get 0.95. So you're going to take 1 minus 0.95 divided by 1 times 100. You're going to have a 5% error. Okay? So it's theoretical, and these are absolute values. Okay? Keep in mind this is an absolute value. So that's what you're going to put here for experimental error. The machine does not give you experimental error. You have to calculate that. So you can do that on the back side of the piece of paper where you have your graph, but somewhere I want to see those calculations. Okay, I want to see those calculations of experimental error, and then you have some questions to answer. Okay, so let's go, get over there, get your calculations of mass done quickly. I will check them, and then we'll start the actual process.